All right, so let's talk about this idea of a function. This is the major theme of chapter 4, and these are used throughout high school math. Use them a lot in calculus, especially these vocab words you see in front of us, domain and range. So basically a function it's a relationship that maps domain values, which are x's, to range values, which are y's, such that each x value goes to only one range value. So an x can't go to 2 or 3 range values. It can only go to 1. Just let's drop by domain and range really quick to get a little more acquainted with them. So as earlier I mentioned, domain's a set of x values over which a function occurs. These are also sometimes called inputs. And if you remember making equations or using equations to generate these values in the tables, you'd put x's in, they'd be inputs. You'd get y's out, these would be outputs. So it doesn't surprise you that the x's are inputs. The domain's also called the independent variable. In sciences, a lot of times this is the variable you change, and then your dependent variable changes as a consequence of that. All right, so range, of course, if the domain is the set of x values, range is the set of y values. These are called outputs. Not a big surprise there. And these depend on what you put in. And so they're called dependent. It's called the dependent variable. So let's get down to the specifics and mathematically look at how you can tell if something's a function or not. So what we require is that each input maps to only one output. It can't go to 2. So -1, that input maps to 1. I don't see -1 mapping to anything else, so good, that's a function. 3 maps to 1. 3 doesn't map to anything else in here, right? 1, it maps to -2. I don't see 1 mapping to any other outputs, so it's only mapping to one output, still a function. And same thing with 4. Now this represents a function because each input only goes to a single unique output. If you look at a picture of it, just plotted a little graph here, there's the input of -1. It has one output above it, right? 1 has one output down here below it. That one input went to one output. And of course, the same is true for x equals 3 and x equals 4, only one output each. So this one is a function. Now, for contrast, if you're still a little confused, like saying, well, how could something not be a function? Let's look at one that isn't. So in this case, we have this input of -1. It is being mapped to 1 here. Okay, we're good. It's a function. Until we look down here and we see -1, that same input is being mapped to a different output. And that is where you have the problem show up. If you look at this in terms of a graph, you have this input of -1 on your x-axis, and your output, these points, you have 2 different points that came out of that one input. That's why it's not a function. The points, the inputs 3 and 4 don't break it. They're fine, right? They only have one output per input. But this point, these 2 right here, make this no longer a function. And just because we're kind of on the subject talking about it, it's pretty typical to have these not be like these discrete points. A lot of times these will be more continuous looking graphs. And so I'm going to just connect the dots here for a little point of discussion. Just so you know, it takes massive coordination to draw lines. That's why it's wobbly. I'm not coordinated enough yet. So look at this. Now there's a thing called a vertical line test, and when you're looking at a graph, you can actually use the vertical line test to decide if a graph's showing a function or not. The basic idea is if you take a vertical line, which are the straight up and down ones, and you draw it, use your imagination, that's straight up and down, just believe me. You draw it over the top of the function. If you drag that line, that vertical line across, it should only touch the function at one point at a time. And so imagine dragging it across, gets close right here because of my wobble, but still it's only going to touch this at one point at a time, verifying that it's a function. Now over here, you might have a graph that looks like, I don't know. If we fill it in, all right. All right, there we go. Now this would not be a function because if we use the vertical line test, we can draw a vertical line, drag it across, but we're going to have a problem right here at x equals -1, right? Because it is touching the graph at multiple points, 3 to be exact. One of them wasn't even shown in the table, the way I'd drawn it. So this, again, not a function. It fails the vertical line test because the vertical line touches it multiple times. And so kind of as we're in conclusion here, why do we care about functions? Why are they a thing, I guess? And so a situation you might look at is just moving objects. And so let's say you've got a graph down here that's representing maybe the miles you've walked as the hours go by. So you start out at 0 miles, and maybe you walk quickly for a while, and then you get tired, and so you start slowing down. Maybe this is the case, right? And so this is a function. At any given time during your walk, you can go find the exact distance you are, or that you've traveled, right? And you're only at one place at a time. Now, can you imagine if I made this not a function, like say it curled back on itself here? This would not make sense for a walk because at this time, what is that, like 6.5 hours? It is saying that you are, about 1.5 miles away, 3 miles away, and about 4.5 miles away at the same time. Now, can you imagine doing that? You'd have to be able to travel in time. It's not possible. And because of this, functions are kind of a natural type of relationship we use a lot, and there's certain features that come along with them that make them handy to use. There's actually a lot of good assumptions we can make if we know something's a function, to kind of make our work easier.